that if any vector is in the kernel, then any scalar multiple of that vector is in the kernel as well. That's this observation right here. Again, remember we assumed V was in the kernel, so we assumed V1 was in the kernel. Here's V1, and we can scalar multiply it by a scalar R, and then evaluate the linear map at L of R V1. And again, since L is linear, that scalar R can be pulled out, and R times L of V1 is just R times 0W, because again, V1 is in the kernel, that's 0W, and so we can conclude if V1 is in the kernel, then RV1 is in the kernel as well. So what have we shown with this paragraph? We have shown that if L is an arbitrary linear map from one vector space to another, then it is closed under both vector sums and scalar multiples. This phrasing should seem very familiar to you now, because those are precisely the criteria that ensure that this collection of vectors is a subspace of V. And that's a proposition. Now, just remember the subspace, the space in which kernel of L is a subspace. Remember that L maps V to W, so the kernel will always be a subspace over here in the domain. Here's another example, which looks very much like the first. L is a map from R3 to R3. L maps XYZ to X03. So in a sense, L is projection 2. It forgets the Y coordinate, which we see right here, and just sends it to 0. So here, L takes everything in the R3 plane and projects it onto the Y, to the X, projects it onto the XZ plane. Then we can find the kernel again in a similar fashion. If A, B, and C is in the kernel, then by definition, A0C, which is the image of ABC under L, must be equal to 0, 0, 0. And so we found the kernel again. The kernel is all points 0, B, 0. Let's make this important remark. This map L is not a one-to-one map. There are many different vectors which have the same image under L. For example, L of 0, 1, 0 is equal to L of 0, 2, 0 is equal to L of 0, negative 10, 0. All of these are equal to 0, 0, 0. So L is, in fact, many to one, it seems. The important points I want to make here are, 1, that L has a non-trivial kernel. The kernel of L consists of much more than just the 0 vector. And 2, that L is not one-to-one. So it seems there may be some connection between the property of being one-to-one and the property of having a non-trivial kernel. Let's explore this. Suppose the linear map L is one-to-one. Under the assumption that L is one-to-one, let's see what we can say about the kernel of L. Well, let V be in the kernel of L. Well, then again, we know that L of V is 0. That's the definition of the kernel. But we know something else that's mapped to 0. 0 is also mapped to 0. So V and 0 are both mapped to 0. But if L is one-to-one, we know that V and 0 must be the same vector. And therefore, we can conclude, what have we shown? We started with the assumption that V was in the kernel, and we showed that V must be equal to 0. And therefore, 0 is the only thing that can be in the kernel. That is, we have shown that the kernel must be the trivial or 0 subspace. So if L is one-to-one, it must be the case that the kernel of L is equal to 0. Now let's suppose, on the other hand, that the kernel of L is equal to 0, and see what we can say about the map L. Under the assumption that kernel of L is equal to 0, let's take two vectors, perhaps distinct, perhaps the same, and assume that their image is equal under L. If L of V1 is equal to L of V2, as we're assuming, then we can subtract L of V2 from both sides and conclude that L of V1 minus L of V2 is equal to 0. And then, using linearity of L, write this as L of quantity V1 minus V2. And so, what have we shown? Under the assumption that L of V1 is equal to L of V2, it seems that V1 minus V2 is in the kernel of L. But we're assuming that the kernel consists of only the 0 vector. And so if V1 minus V2 is in the kernel, the only thing it can be is the 0 vector. And therefore, adding V2 back to both sides, we obtain v1 is equal to v2. That is, let's summarize. We've shown, under the assumption that L of v1 is equal to L of v2, it follows that v1 is equal to v2. But that's precisely the definition of L being 1 to 1. So it seems that if the kernel of L is trivial, then L must be 1 to 1. And so these two facts are essentially the same property of a linear map. If L is 1 to 1, it has trivial kernel. And if L has trivial kernel, then it must be 1 to 1. That's a theorem, and we'll write it here. Let's conclude with one final example and an observation. Let L map R4 to R2. L is defined as follows. L maps the vector A, B, C, D to A plus C, B plus D. And let's see if we can determine if L is 1 to 1. Well, by the above theorem, all we need to do is look at the kernel. And if the kernel is 0, then L is 1 to 1. If the kernel is non-zero, then L is not 1 to 1. So let's see what we can find out about the kernel. Assume that A, B, C, D is in the kernel, as we've done here. Then we obtain A plus C, B plus D is equal to 0, 0. After all, this vector is the image of this vector under L. And if we're assuming this thing is in the kernel, then this must be equal to 0, 0. And so from this vector equation, I just equate the first and second components, and I obtain A plus C is equal to 0, and B plus D is equal to 0. So if I take these relations and make the substitutions, I see that my arbitrary vector in the kernel, this one right here, can be written as AB, negative A, negative B. After all, A is equal to negative C and B is equal to negative D. And then I can factor the free variables A and B out and write this as A times 1, 0, negative 1, 0, and plus B times 0, 1, 0, negative 1. So this is a complete description of all vectors in the kernel. We know that the kernel is a subspace. Evidently, these two vectors, this one and this one, span the kernel, and it's easy to verify that these two vectors are also linearly independent. That's a separate check, and it's not completely obvious from what we've done here, but it's true. So what have we found? We've found a basis for the kernel. That basis consists of more than the zero vector, so we can conclude confidently that the kernel is not the zero subspace. It consists of much more. Here are our conclusions. 1, the kernel L has basis consisting of these two vectors. 2, therefore, the kernel L isn't 0. And 3, therefore, concluding from our theorem, L cannot be 1 to 1. In the next video, we'll look at another very important subspace associated with the linear map called the image of the linear map.